Hello again and welcome back to my continued series of Advent of Code in assembly language. In 2025 I used MIPS assembly targeting the PlayStation 2. So this will be an introduction to how I set up my templates for doing the solutions, and maybe even a bit of a introduction to assembly programming for the PlayStation 2. So firstly, the assembler I used. I used this Nakin assembler from Michael Cohen. You can find it on his website, Nakin ASM. It supports a wide range of CPUs, including down here the Emotion Engine and the Emotion Engine VU, and even the Nintendo 64 RSP if you want to use it for the Nintendo 64 as well. Along with the assembler are a lot of samples, and you will see that my template is based off some of the samples here, particularly the triangle ASM. There are quite a few comments in here as well. But then along with that assembler, you will also need a lot of documentation for the PlayStation 2. One good resource is the PS2 Tech page, which has a lot of the memory map registers listed, and especially we see down here the SAF, the SAF I think. Is it SAF? No. Where were we? IOP and peripherals I think. Here we are. IOP and peripherals, the SIO2 port for the controller. We have all the registers that we need to talk to for controller reading here as well. We'll come back to that a bit later. And you will also need, if I think this one here, yep, documentation, PS2 documentation. I think you can find these on GitHub as well, but especially you'll need this EE Core instruction set manual, the EE Core users manual, and the EE users manual, the GS users manual, and the GS users manual supplement, and the VU users manual as well, particularly if you're using the vector units. Along with those, you also need a good emulator. The best one for the PlayStation 2 is PCSX2, which honestly is not a very accurate emulator, which is a problem. It will allow you to do a lot of things like memory reading in locations that the hardware will throw exceptions for, so it's not very good, but it's about the best you can get. And it does have debugging options, a full debugger, so you'll need that as well. Alright, so that out of the way, let's have a look. Let's start looking at my template, shall we? So let's bring up the NeoVim again. So the first thing, we've got a bunch of includes here. Most of these, you see the registers ones, are just defines for register values or register addresses, and some values defined as well, like the system call values. Right? There's no like big functions, big subroutines hiding in these includes. The macros one, we can see an example of a macro down here which I made based on some of the macros there. Basically, a lot of the configuration and values require you to pack values into, say, one 64-bit number or one 128-bit number to send to a register in the Emotion Engine or the graphics synthesizer. And so these macros are a way of packing that data more easily by just listing the values, and the macro will pack them all together for you. So that's what we've got going on in this macros include, and in my one down over here. The VIF is much the same as the ones up here, the system calls, the just defining values for or defining variables, two values, so that you can, what's the thing? Dividing these words to values so that you can reference them easier. Got some exports up here which mostly help in the debugging phase. You can find places in code easier. And then some of my defines down here. The SiO2 registers, I've got those all defined down here, and some SiO2 values. I don't really use those, that's fine. We'll come back again to those a bit later. I think most of these I ended up not using, that's fine. These I stopped using as well, but I had some defines for color values and defined some memory addresses as well. Most of my memory takes place at 20,000 hex, or 200,000 hex. That's just my choice. The entry point, you see down here, the entry point is 100,000 hex. Everything like above that, if we go back to the memory map, I think everything above that is kernel space, which you can't use. So at 100,000 hex downwards is user space in the memory, and it goes up to, see the stack pointer here, goes up to 2 million hex, which is 32 megabytes. That's the top of the system RAM for a standard console. If you happen to have a debug or dev console, you might have, I think they have 64 meg or maybe more available, so you can put the stack pointer further up, but this is where you stick your stack pointer for a normal console, for dev work, for a normal console. So we come in here into the code. First thing we've got DMA reset, right? We're going to jump to DMA reset. Let's have a look. Let's go to them as well, shall we? So the DMA reset, we're setting lots of zeros. We're particularly resetting channel 2. I put channel 1 in here, but I ended up not using channel 1. I'd have to look to see what that is again, but channel 2 is used for transferring data to the graphic synthesizer, the GIF. So we reset channel 2 by setting zeros into a lot of things, setting up some default values into the status, and then zeroing out a lot of the DMA status, like the overall DMA engine controller, DMA controllers values, set those up, and then we enable it again. Right, then we go back. So let's see. I'm doing the wrong thing. Yeah, we're back here. So reset the DMA, then we reset the graphic synthesizer, right, and we set up the interrupt mask register. These are done through syscalls. So syscalls are basically telling the kernel to do things. So this is something different from like the GBA or even further back the NES, where on the PS2 you've actually got a kernel that's running sort of in the background that has most of the high level access, and you have to tell it to, well, ask it to do things for you. So we set up an interrupt mask register. We have to put these values V1 and A0, and you can find, I think it's in the manual somewhere, which registers you need to put values into for each type of syscall that you want to do. So V1 there is the syscall, which is gs put IMR mask register, and A0 is the value that you're passing to put into that register. And then you call the syscall, and the kernel goes, okay, in this register stick this value, right? And then it will drop back to here. Then we are setting up the output for the graphic synthesizer, and this is done through the syscalls as well. The same sort of thing. V1 is the register we want to set, and this one takes 3 values, so A0, A1, A2. And we're going to be setting up non-interlaced, NTSC, and the frame field is not used when it's not interlaced, so it doesn't matter. We pick a frame buffer read circuit. It could be either 1 or 2 or both. We can put 1 and 2 together. I'm using 1. I think most of the time the Nakin examples, they use read circuit 2. It doesn't really matter. I think if I remember correctly, if you want to use a background color, you have to use read circuit 2, and then if you're using the two together, then read circuit 2 will be the background and read circuit 1 will sort of overlay that, and you do a transparency through read circuit 1 to get the background color showing through. But I'm not doing any of that. That's fine. We can use 1 or 2. It doesn't matter. Come down here. We set up the frame buffer. Where the frame buffer is in memory, I believe, and the size of it. And we also choose here our pixel storage format. This is something you'll have to read in the manual as well. The PS2 has a number of pixel storage formats, the same as the PS1 actually. You can have ones that use a C-LUT or CLUT to have something like 4 or 8 bits per pixel. This mode here, I've got 16 bits per pixel. You have 1 bit for the transparency, and then 5 bits for each channel of RGB, and then you have the 32-bit per pixel. I think there's a 24 as well, but I have to go back to that. 32 bits per pixel, so that's 8 bits for each channel. Transparency, RGB, and then you set up the width. So you see the frame buffer width 10 is 640. I've got 5, so that's about 320. I end up doing like 320 by 224 or something. And then the position, XY position. That XY position is like XY position in memory, in the video memory that the frame buffer exists at. So this one here, we don't have to syscall it, we just set it straight to the GS. And then the display, set up display as well. This is where we're using my macro. So these values here, see the last one here is just in pixels, the height, so it's 223 or 224 minus 1 for the height of the output. This film here that's in vector units, that's a little bit harder to work out or discover what it is, these sort of vector units, raster units thing. Actually, if I can show you, it's this one here, isn't it? Bring up Notepad. I found these modes in, I think it was in where was it? It was in the emulator, I think, in the PCSX2 source. Here we are. These are the sorts of modes that you can choose from and the values that go with them. So you've got the XYs and their width and their height. Let's see if we can get a bit of a look of what these things are, or what they work out to. Right, so let's see, where are we? It's a bit harder to make out where I've actually got all of these things at. Where are we? I think part of it was up here somewhere. So here is where we've got the mode, the video type, I think it is, right? That mode value in the column. So you got NTSC is mode 2, 3 is PAL, it's actually in hex. So you got 50 for 480p, 53 for 576p. It depends on your BIOS versions. 52 for 720p. Right, these are these modes. Can I do? No, I can't do it like that. And the sort of resolution modes are all there. Right. Then we go down to here, and we get these. Here is your width and your height. The width and the height in the columns here, width and height. Right, DWDH, width, height. Right, so we do -1 to each of them. You got your two values here. Right, and then the X and the Y's are essentially the ones down here, but you can make some changes to these depending on what actual resolution you want. So this one's a bit larger than is up here, but it's okay, it works out. But these are sort of your XY's for your DXY here. Right. These magnification, horizontal magnifications, these are dependent on your actual resolution here. But you also have to look those up a bit. Anyway, so that sets up the display. That's gone. Good. We store that over across there, and the next is the installing a vsync handler. So this is, let's go down to it, shall we? Not that one. Shouldn't have had these so long. Again, this is a syscall, so the kernel is handling the syscalls. Not the syscalls, the kernel is handling the vsync interrupts, all the interrupts, right? So when an interrupt fires, the kernel collects it, and so if you want to have if you want your program to handle an interrupt, then you have to register it with the kernel, and that's what we're doing here with the vsync handler. This is the register that we're going to call, or the whatever it is we're going to call. It could be a subroutine actually. This is, so I'm going to set up a vblank for the start. It's a vblank S, that's the start of the vblank. Vsync handler is down here. It's this address, this part of memory that we want to jump to when to handle the interrupt. And I think the last one, A2, is essentially we can just leave it at 0. So send that off to that syscall, and it registers that vsync handler, but it isn't enabled yet. You can see down here I've got a subroutine to enable the vsync interrupt handler, and one to disable as well. Sometimes you want to disable it too. And then I've got my vsync handler down here. May as well have a look at the vsync handler while I'm here. So one thing that happens when the kernel catches the vsync, catches the interrupt, it will back up all of the register values to, I'm going to say all, but at least all the ones it uses, to the stack before it launches into the vsync handler. The kernel will do a bunch of other stuff as well. I haven't tracked all of what it does, but it backs up most of the register values into the stack before calling the vsync handler subroutine. So, but then I'm backing them up anyway, whatever the values are. I guess I pretty much don't have to do this, but who cares. Then I call the update result, which is going to take the values that are in the results and then convert them into the output data. and then it's going to send off 2 sets of gift packets. It's going to update the text, and I don't know exactly why I update the title text every frame. I probably don't actually have to do that, but who cares. And then it's going to update the tile data. Tile data holds all of the changeable text in memory, which is going to be the result that goes on screen. And then it will clear the interrupt. We've got to clear that interrupt there, and then return out from this interrupt handler. Alright, so let's jump back up like this. So we've installed that vsync handler, and now the GS is ready to start. See, this is here you can set the GS BG color. Again, I think that was with frame buffer 2, or the output circuit 2 mainly. Here's some stuff I didn't end up using, but this was setting up the VIF1, which is the vector unit that's sitting next to the GS. But again, I didn't actually end up using it. Who cares? Now I'm going to clear the screen. I'm going to start my program, so I clear the screen. Let's see, let's have a look at clear screen, shall we? So again, you know, we're setting up, we're backing up register values to the stack. Well, first we subtract the stack pointer. So we move the stack pointer up. How many values I think I'm going to stick into the stack, and then we stick these values into the stack here like this. And I always store them as doubles. Usually I'm not using quads most of the time, and so doubles works fine. Yeah, makes sense easy enough. So clearing the screen, we grab these values here into A0, A1, black screen end, and then we jump to the GIF send data. One thing you have to be careful of using Naken or any assembler really is that a lot of these allies here will end up being converted into two operations, into two operations, because of the way that you load values in MIPS. This is actually a thing that happened with ARM as well. But in MIPS assembly, when you do a jump or a branch, the next operation will execute before the branch is taken. Which is why I've got a no up here. So you might be tempted to put this li after the jump, so that it gets loaded into that register before the jump is taken, and so you're not using a NOP that you don't need when you don't need to. However, if it gets turned into two operations, then you'll end up like loading half of the value into A1 before the jump is taken, and then the other half of the value once it comes back. And that's a problem. You end up like loading something into memory, trying to put something into memory, or reading a lot more out of memory than you were expecting to. So you had to be careful about that, especially using these allies, load immediates. Most other operations are exactly as they appear. So like a SD, like a store double, or load word, an LW or an LB or an LH, right? Or if you're doing, I think if you do like an LI and it's less than a 16, I might should check on that again. I think it's less than 16-bit or a 16-bit number with an LI, then it's then it will do it in one operation. but especially like things like memory addresses, you got to be careful not to stick them after a branch or a jump, unless you know it's going to be one operation. Alright, so we load these two addresses effectively into A0 and A1, and then we jump to give send data, which is right down here actually, give send data. You can see I've got a comment here that A0 is the address in memory and A1 is the end. And so in give send data here, of course we're backing up registry values again. We load channel 2, the DMA, and we jump to the DMA wait, because if the DMA is busy we have to wait until it stops being busy. You can see here that I actually have a sub here after the JAL, because it'll take one, it's just a single operation, and you know, we can do it before we go to the DMA wait. It's fine. So this is subtracting A1 or A0 from A1, so this ends up becoming the length of the packet that we're going to send to the GIF. And then we have to shift that to the left by 4 places. It's effectively divide by 16, because the length that we want to send to the DMA controller is the length in 128-bit blocks, which is 128 bits is 16 bytes, and so we divide that length by 16. So when the DMA comes back, I don't know if the DMA wait is close by, probably not. So when the DMA, when we come back from that DMA wait, we send those values to the DMA controller, and then we start the DMA controller to send that GIF packet, and then we wait for the DMA again. Now I can probably have actually stuck this word below in here just to save that, but who cares, it's right. And then we're loading up back our values out of the stack and restoring the stack pointer. Alright, so that's the black screen thing. Let's have a look at the DMA wait, and then we'll have a look at this black screen end thing, because we need to have a look at that. Let's see, where are we? Oop, there we are. Not that one there. There we are, down here, DMA wait. Okay, so this one here, I call it with the DMA channel in V0. So you can wait on any DMA channel. It's just whatever channels in V0, addresses in V0 when you call DMA wait. Only use S1 in here. We load S1 from V0 and we're waiting or we AND it with hex 100, and if it's not equal to 0, then we stay in the loop. Yep. And then we jump back up. So that's just the DMA wait, very simple, very short. I think I shortened a bit from the sample one. That's right. Okay, so the black screen. So, oh, here we are. So here is, at the end here I've got a bunch of stuff you can see already. I don't think I used the text mask in the end, that's fine. We've got these controller poles set up here already. Controller polling, you send like a packet like this. The length is the size of the return as well, so this controller pole here, that's 5 bytes in length, you get 5 bytes back. This one here, which is controller pole DS2, that gets you the analog stick results as well. So it's 8, was it 5, 9, it's 9 in length, and you get 9 bytes back. Config on, config off. I was using those trying to get the control thing working. It don't end up using them again. That's alright, they're there. Anyway, so we come down to the black screen here. Right, so these are GIF packets that are already pre-set up. I've made some changes to this one coming from the samples. But there's just sitting here set up in memory, so I can just use them as they are. I've got a bunch of these down here. So you've got the GIF tag header first. Seeing it's going to be packed, right? So these are all macros as well. These are all macros that are set up. This is the register it's going to be placed in, and you'll find these in the GS documentation. These register names. So these are packed GIF packets. They're 14 in length, so if it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Right, 14 128-bit chunks. Right, so there's DC. Sorry, let's put that in there. There's a DC64. You got one value and then a second value here, so it's 128 per line. Right. So we've got the frame buffer config over here. We're setting up the size of the frame buffer, the size of the Z buffer as well. You see here we've got the pixel config as well sitting in here. These XY offsets are not actually that important. You can basically set them to 0 or any sort of value you want, I think. But the shifted across 4 because it uses, I think it uses fixed point. So the last 4 bits are a fractional, so you've got to shift them 4 to the left. We've got the scissor, which is basically the size of your screen, right? So it's 320 by 224. So you got sort of your upper left and your bottom right positions, X, Y positions, X, X, Y, Y sort of thing. Something like that. And then some other mode things in here. Most of these are just copied, you'll see them the same. I wanted a black background, so you can see here. Here we're sending a primitive, a sprite, and the sprite is going to have a black, just going to be black in color. And then we're setting like the positions of it, the X and the Y coordinates that make the well, the top left and the bottom right positions. You can see it's using here the same values as up here to be the top left corner, and then these values down here for the bottom right corner, which are probably these ones here actually. That's right, whatever it is. And then that's the end of that GIF packet. And I've got a bunch more packets in here. We'll go over these just quickly as well. I did have a VPU packet in here, but ended up not using it. That's right, just sitting there. A GIF packet here for the GF tiles. These are for sort of each value that I generate to send to the GIF from text. There's one packet is the information for it, and then the second packet is the image. So we've got the first one is like where it is in memory, what type of pixel format, where it should be stored on the screen, I believe. Yep, where it's stored on the screen. The size of the image, so it's 16 by 16 images in this case. Right. And then these ones here are predefined images that I created, and I actually built these using a Python script to create little blocks, strings of text using this pixel format that I want to use. That 16-bit per pixel format to make those blocks of text, and just prepare them in these binary files that I can include. Much easier than what I found at one point. I was generating all the text and then loading the byte, like loading the characters from a font and like putting them all together and then putting them to the screen. And I think the amount of time that takes, computational time it takes, right, it wasn't worth it really. You can save a lot of that time just by pre-computing that and storing it in binary files, which you can include here, and then just like send those memory addresses to the GIF, right? To my GIF, was it send to GIF, a GIF send packet sort of thing. Made that a lot less time, a lot easier, a lot faster. So I've got one for like the day header, so day, the gold, the silver headers, right? Silver colon, the gold header, gold colon, the done string, done, and a way to clear the done string as well, which you just have like 4 spaces, an empty string that's 4 long. But I also did include these fonts, these font files that I made using those pixel format, also using Python scripts. We set the day number and include the input at the end here, and that's like all these includes that I have at the bottom. Okay, so where we were at, let's go back up to the top somewhere. Alright, so we have cleared the screen. We cleared the screen. Swoof. We're getting there. Okay, we want to clear some RAM in where I've got input buff, where I'm loading in. This is where I put most of the where I load the controller data and where the results are stored. I clear that out at the start, and then we are setting up the tile table. I use setup tile table. Well, I call it setup tile table. It's mostly doing sort of this tile data here, which is all the variable tile data, all the variable text, the day number, and the values for the results. They go into memory, and the default values go into here. So on day 1, it'll put 0, 1, and then fill out all the zeros for silver and gold in this part here. Then we seeing day title and to day gold title packet end is all one big block at the bottom of the input. I can use that as the start and the end and send that GIF send data, all that, and it will send all those packets in one go to the GIF, and then we send the tile data to the GIF. And then we enable the vsync interrupt and we go into the actual program. So let's have a look at the set up tile table. How do I call it? Set up tile. I have to do some in. There we are. Okay. And to get the case correct. So stack, we load in tile data. That's the start of where we're loading tile data. Actually, in memory, the day number comes first, and then the gold result comes next, and then the silver result is last. And then I work backwards when I'm updating it. We do the silver from the bottom up, and then the gold from bottom up, and the day doesn't have to be done. So we jump to the setup day tiles. First is to the day number, so that's the value that's going to be in there, or where day number is a reference that points to the value that's going to be in there, right? So we go set up day tiles. That's the one done here first, right? So we get the GIF tile, so and GIF tile end. So and then we've got the X position where we want it to be stored in the X position. The Y position comes in on S1, right? And there's going to be 2 tiles that get set up here. So we copy the GIF tile into memory at tile data. So we do that by loading quads. We're going 16 bytes at a time, and then once we get to the end of that, we fall back out into this part here. We've got load this 512 here, and we load this into back into S2 from the stack pointer. S2 was the day number, so we get the first byte from day number, which is usually a 0, right? 0, 1, 0, 2, 0, 3, 0, 4, 0, 5. Usually the first one is 0. Then we add 1 to that pointer, so we'll get the next byte next time. And we store that back into the stack, because we can then use S2 again. So grey ASCII, we want the daytile to be grey. Right, so we load that into S2. We subtract 32 from S3. Remember, S3 is this byte value here. I think that gets us. So we're going from the ASCII representation to just the hex representation. So let's say a 0 is like, basically we're subtracting off all of the sort of unused ASCII characters, which I don't have in the font table, right? And then we multiply that by S1, because in my font table each character is like 512 bytes, right? So if the hex value, right, of the character that we want to print is 10, then we want to multiply 10 by 512 to actually get to its position in the font table. I've got a sync here. I don't think I actually need the syncs, but that's right. And really, seeing I know it's 512 here, I should have not used mult, I think, and instead used a shift, which would have been faster. But that's okay. So that's a mistake that I should have thought of, right? And then we add the position. We add that value to the position in memory that the font table is at, to actually find that character's position in memory, right? And then S3, we add 512 to it to get the end of the character in memory, and we're going to copy that character from the font table into the tile data. Right. And after that, we want to load the XY positions back out of we'll load some of these positions back out of the stack, and store the XY position for that character where we want it to be on screen into the GIF header at these offsets 36 and 38, right? And then we prepare these GIF tiles headers again, and if we're not at the end of, oopsies, if we're not at the end, because S5 is how many titles we want to copy, right? If we're not at 0, then we want to go through it again one more time. We add 16 to S4, which is our X position. So the next tile we want to be shifted over by 16 pixels, right? So I'll do that twice, and that's essentially how the day tiles, the num tiles works as well for silver and gold. essentially the same, except we're doing 16. We start at a different X position. They give us the Y position on the way in. We're always using the character 0 for the silver and gold, and when we're setting it up, we're always using character 0 for silver and gold. So we always use at hex 2000, but otherwise it's the same thing. Alright, so that sets up the tile tables. Oof. Okay, we're getting there. We're getting there. So we've enabled the interrupt. So we set up these input buff, input action. We set them to 0. Right. What we've read from the controller gets set to 0, and what action we think we're doing, we'll set that to 0. We zero those out. And we've got our action loop. This is looking for input essentially. We'll start up waiting for the VSync. We don't want to be checking the controller like 500 times a frame or more. Not important. Jump to the controller read, and this is a point here where we can actually load this value into T1 in the branch delay slot, because it's just a 16-bit value number, so it's fine, it works. And then we're going to check to see if we got that 1100 hex result from the controller read. This is checking because, especially at the beginning, I couldn't get controller reading working, so I wanted it to run automatically. Like if there's no controller connected or it can't read the controller, just run the solution, right? So that's what I had set up. This one here, it doesn't really matter that we have this load afterwards. It's not necessary for this branch. So we can, even though this one here would become 2 operations, it kind of does not matter for this branch. So that's alright. Then we're also checking if we've got the correct report back. Alright, because they should get a 5A4100 or something. So we load a word from there, we AND it with this here, and if it's equal to that, if it ends up equal to that, then I think actually, if I remember correctly, the expected result is well, 5A41FF, and when I got controller reading working, the top bit came back 0, and so it wasn't FF, it was like 7F 415A. And that could be a misconfiguration of the SIO2 when I start the transfer, but I didn't bother to investigate fully on why it came back like that, so I just don't care about the top byte. So long as the rest is 415A, it's fine. It's a good report. Good enough. Right, so I don't check that top byte. And so then I've got here, I'm checking for a reboot, select button to be pressed. If it's a select, then we reboot, boot back, restart back to the it's a soft reboot back to the, what do we call it, back to the menu, the OSD sys, right? We've got this syscall here. If it's the circle button down here, we check for the circle button. If that was pressed, then we jump to the run solution. Otherwise, we just go back into this loop. So we'll skip over this run solution stuff here for now. Let's have a look. And we've got this no controller as well. Just ignore mostly. Yeah, if there's no controller, you want to wait instead of restarting, right? Because if you come out of this, if there's no controller and you automatically drop into this run solution, when the solution is finished, if you just jump back to the action loop, then it'll start the solution again, right? So what you want to do is if there's no controller when you finish the solution, you just want to sit here instead of going back into the loop. Anyway, let's check out the controller end, because this is the fun part. This is the thing that took me months to work out, because it didn't work the way it looked like it should work. So we've got here, we'll reset the SIO. We've got an idle value which I set up here. The idle value 3BC. Right, we send that to the SIO. Then we set up these send 1 and send 2. We send to these values. These values I got from my console. I dumped them, like I ran a sample program here, and then before doing anything with the controller, I had it print out these values, collect these values, and print them out from memory, so I could see what the previous program, FreeMIC boot, had last set those values as essentially, and I use them as these are what I know the console sets those values to, or what other programs set those values to and work, right? So you set those and send 3. So send 1, 2 and send 3. We set up these values here, these particular values, and some of these values which I'll actually bring back in the browser. If I can bring that in on top of over here again. If we go back to the IOP and SI2, you see send 3 is the length of the report that we're going to be sending. You can have up to 16 different commands. Doesn't matter for that. We're just doing one console poll. Peripheral bytes. We can do that for now as well, right? So is basically, I think it says fake command length and real command length. I think it's really the send command length and the receive command length in the end. But as you can't really see here because it's in hex format. It's essentially like 055 or something in those values there. Then we have the command to the controller. So the FIFO in, I want to send 5 bytes to the FIFO in, and we're sending this controller poll, which was down further. So if we go to FIFO in right, where are we? Here we go. SO FIFO in right. And we look back at the browser here. Sorry, wrong one. SO2 registers. We got here FIFO in. Right, it's a 1 byte register used to upload commands to the SO2. And we've also got down here actually. There's some memory cards. The controller commands are here, right? So packet header has an 01, a command byte, and 00. The reply it starts with FF, and then this is the command byte again, 51. So say 41H is the mask reload. 42 is the one that we want to use, right? So if we want to send a packet for reading the controller values, 01, then 42, and then we need the header byte and 2 button states. So 01, 42, 00, 0000. Right, and that's your command that you're sending. Right, so we need to send those bytes to the FIFO in here. You can use the DMA as well, SIO2 and DMA, but this worked for me, just doing that manually myself. So bring back NevIm again. If I can do that, click on it. Right, so you see here we pick the FIFO in, and then I go through this. My source is S0, the length of the S1. So we're loading bytes from S0, which is my controller port, and we're looping through S1, the length of S1, and we're storing those into FIFO in, right? And then we drop back out. Okay, and now we're going to start the transfer. So we reset the interrupt. I've got an interrupt reset down here, right? Prepare the SIO interrupt. We've got the address of the SIO interrupt. This is the mask we use. I believe it's just this this bit here is the interrupt for the SIO2. Let's see if I can find that, shall we? So 1F, what was it? 801070. 1F. Here we are. That's the status, interrupt status, and here we go. So you see down here, we've got the mask, well, the stat and the mask, these use the same bits, so it's alright. SIO2 is down here. So bit 17 will probably work out. Oh, you can't see it. You can't see it, of course. NevIm down here, boom, there we go. IOP interrupts, right? Is the istat for the interrupt status. And down here, IQ17 is SIO2. And that will result as being this bit. Yep. And we just store that back into there to reset it, essentially. Right? This just prepares it. You can see down here as well, my interrupt. Right? So we've set up the interrupt, prepared the interrupt, and now we need to send. Now we need to send the command to the controller. We need to poll the controller itself. Get the SIO2 to poll the controller. So we load this word. So what I'm doing is that I load the state of SIO2 control, which usually it's actually in a resting state of basically this value here, I think. 3F0, or is it 3B0? I think it might be 3B0. Is its sort of resting state. If you load the value from SIO2 control, you get that 3B0 most of the time, right? And what you would find, in fact, I'll go back to the browser for a second. SIO2 command sequence, got the command sequence here. If you go up over here, right, it says that the 0-bit seems to start the command transfer. The interrupt is raised after touching this bit, presumably the command is completed. Bits 2 and 3 reset the SIO2, preparing it for another transfer. The rest of the bits are unknown. Now, and you can see it's all in this one here, the SIO2 man module in the BIOS sets the register to 3BC after on a reset. Now, what I found in trying to do this manually is that if you just set bit 0 to 1 to start the transfer, it does send the interrupt immediately after touching that bit, but you don't get a response back. You just get a blank response back. Just get FF for everything, and the default state for this peripheral response, just in its default state as well. So what I found is actually right here. It's actually this. You have to set bit 0 and bit 1. So send 3, right? So I OR it with 3, and then set that, and then it actually sends the response, the poll to the controller, and you get a response back. And from my, as you see, I've got an interrupt wait here. From looping through, or from counting inside this interrupt wait loop here, it usually takes between 250 to 500 iterations of this loop for the response to come back. I do have a timeout in this loop for 1024, just in case something happens and you get stuck. But there is some variance in how long it takes for a response to come back, so you've got to be prepared in that. Got to be prepared for that a bit. And it will, I think, what have we got here? Yeah. I store S0 and S1 and S0. I think that's clearing the interrupt at the end once S0. Wait, what is S1? Oh no, right, I load S1 from S0 here. Right. Because when you want to clear the interrupt, you basically put the value back into it. So when I load the value from the interrupt, we AND it with this value here. If it's equal to 0, well, if S2 is equal to 0, right, this count is equal to 0, then we'll escape out, right? Otherwise, there's check run from it. If that is equal, if the value that we loaded from the register is the interrupt register is equal to this value here, then the interrupt has fired, and we store that value back into the interrupt register as we escape, as we exit, to clear the interrupt. Yeah, so that reads the controller. Like, you know, it took me months to work out how that works. But the thing is, I mean, I looked at PCSX2's source code, and I looked at PS2 dev, Padman source code, and they all only touch bit 0 to send the controller, to send the poll to controller. And exactly why I need to do bits 0 and 1, I'm not entirely sure. But I mean, I asked ChatGPT, and the thing is, it couldn't give me a source that specifically gave the information and gave the reason why. But it gave an explanation that is plausible, and so I will mention it. Usually when you're using like Padman or whatever programs, you use a module that's in the IOP to poll the controller, and you'll it's running a server, and you request to that server to get a controller reading, and that software that's running on the IOP, that module that's running on the IOP, will do this command, will send these commands to the SIO2. And so the response from ChatGPT is essentially that when the IOP sends the command to the control register, it essentially automatically triggers the bit 1 as well as bit 0, just because of the way it's set up internally. But when I'm doing this from the Emotion engine, when I'm using the main CPU to send these commands to those registers, it doesn't automatically set that bit. So long as it's running on the IOP, you just have to do bit 0, and it would automatically do bit 1. And so it's possible that that top bit on coming back as a 0 instead of the expected FF could be another value in that control register that would be set automatically when the command is sent from the IOP. That's my thoughts on the issue. But I have not looked further into it. ChatGPT could be completely wrong, but it makes some sense. Anyway, this works for reading the controller, and so we can go beyond that. Everything's fine. So then we jump into the SIO FIFO read out, or out read. So we have to read the bytes out of the FIFO. We've got down here, we've got to read 5 bytes out because we sent 5 bytes to it, right? And so we go here and we loop reading bytes out of the FIFO for SI2 FIFO. I also have, I think over here, I read out the value from receive 1, which, if we look at here again, is the status, the peripheral status. So like we'll have a 1100 if there's a connected controller, otherwise we'll have something like this, 1D100, or I think there are some other values as well, like just 1000 hex is like a default value too. So we read those and we store them into the input buffer in memory. So that's reading the controller. So that's most of what we've got going on up here. I guess there's one more major thing that we need to look at. I've got here to show the done message. That works the same way as the clear screen. We just load this done title packet and we send it off to the GIF. There's one other thing down. I think we want to have a look for. Is at the start of? Oh, here we go. I think it's here. Reset result at the start of solution, and is it reset result that I'm looking at? And the vsync wait at the start of the solution there. Here we go. Let's have a look. Yes, here we are. So reset result is going to clear out the silver and the gold result, and then do call update result. I've got a lot of store zeros. Okay, yeah, that stores the silver, and then that one there clears the gold part, and then we also clear the done message, done clear packet. Gets sent to the GIF. Okay, so I think update result is the main thing they want to look at last. So we have update result here. So for this one's it's kind of weird. We're using tile data end, so we're going to work back from the bottom of tile data. We're loading the value from silver result here. We're going to be dividing by 10, right? Because we want the last digit of each of it in decimal format. There's going to be 16 values, so we use 15. Don't worry about it. And silver uses the white ASCII font, right? So we jump to division 64. then we'll go through division 64 in a second. We add or subtract 608, which is the length of a GIF packet in memory there, to S0, which is the tile data end. Yeah, so essentially moving to the start of the last, start of the previous GIF packet, right? And then it will, from the value that we get out of division 16, it will update tile, and then it adds 16 to S3 here, which I believe is the going to be the X coordinate as we move across. And then we've got a double add. And what am I doing here? S5 into S3. I think I'm doing something silly here because I'm storing this into S3 as well. So what am I doing here? This isn't being used. Anyway, okay, whatever. And then we've still got the update silver loop here. We're subtracting 1 from S2 each time. Right, so we'll have to do a look at division 64. So the thing is, you can have some really big numbers for the results. So sometimes I need to divide by a 64-bit division, and sometimes if I can get away with it, then we can do a 32-bit division, which is just a single command, right? So we check the upper bound, upper 32 bits, to see if it's greater than 0. If it's not, we do a short division. We just do divu to divide the value by S1, and we get the results back. Yeah, that's sort of odd there, isn't it? That I've got that add and then the thing on there. That's weird. Wait a second. What am I doing there? So add 16 to S3 and store in S3, and then we add 0 to S5 and we store it in S3. What? What am I doing? That's just essentially adding S5 to S3, isn't it? Except it's a double addition. Yeah, I don't know what I'm doing there. This makes no sense. I think update tile may actually take care of S3 has the digit. Oh no, wait a second. Yeah, okay, sorry, because this addition here takes place before we take this jump. Then once we come back from that jump, this one here will go. So S3 will become the value that was in S5. So this is essentially like a move the value of S5 into S3, except that it's a double. The value that's in S5 could be greater than 64-bit or greater than 32-bit, and so you have to use a double add to make sure it goes into there. Yep. So okay, we know what I'm doing there. All right. So if it's a long division, the way we do this is that because the value we're dividing by is 10, it's less than 16. It's a 16-bit value number. It's less than 16 bits. We can split the 64-bit value into 16-bit chunks, and the remainder that we get from each 16-bit division, we can move into the top 32 bits, the top 16 bits of the next division, next stage of the division, right? So if you chunk it into 16 bits, we do 32-bit division, and the remainder goes into the top 16 bits of the next round. Right, so this is going to go 4 times. You got it 48 here. So we start off by shifting 48 bits to the right. Sorry. Right, shift it to the right 48 bits. We AND it with this thing here. So if there's anything above that, we want to get rid of anything the 32 bits above that. Anything above that 16 bits that we want to do, we want to clear those off. And then we shift this thing here, our remainder from the last round, we shift that left by 16 bits and we put them together. And if it's 0, then we don't have to do anything this round, right? We just go to the next round. Otherwise, we do a division. We take out those the remainder and the quotient and the remainders, and we go into the next part, right? So then we go shift it. We have to shift it back to the left by the same amount that we did up here. Do an OR here. So we have to stick, was it the sticking T0, we'll OR it with T5. The quotient that's sitting there, it's probably 0 anyway. And if it's not equal, if T4 is not equal to 0, then we're not finished yet. We subtract 16 from it and we go through the next round. Right, we go through the next round, and then we get these. This is again, we're moving these values, our remainder. I mean, we probably shouldn't need to use dadd here for the remainder, the final remainder, but we do need it for the final quotient because that could be above 32 bits in length. But so it does 4 rounds of division like that, and we get out a final remainder and a final quotient. For the next division, that will happen. Do the next, the next value, the next digit. So I'll do that 16 times for silver, and then do update tile for each of them, and then 16 times for gold, and update tile for each of them. Stepping up through the values in the tile table, tile data. 608 bytes each time. Right, and then we sit down here, we'll update the tile. Right, so this does the same thing. So we're using the font is in S4. The digit that we want to put onto screen is an S3, right? So we multiply that by 512 to get the the digit in the font table. We move past the header, which is 96 bytes in length. We get the end. We get the actual position of the start in memory of that character in the font table, and the end of it, and then we're just copying out 16 bytes at a time into the table, into the tile table. And when that's finally done, I'm going to go on to the next one. So that's copying those in there. We've gone through those, gone through the VSync waits, the VSync handlers, the interrupts, the DMA resets, and we're basically done. Hooray, we're basically done. Alright, so that's my introduction to PS2 assembly and MIPS. Or should I say, yeah, PS2 assembly, MIPS assembly for the PS2, I guess. Next time we'll go into day one and we'll explore the day one solution. Alright, that was quite a long one, and I hope to see you again in the next part.